Good afternoon. I'm Melvin Oliver, president of Pitzer College, and it's my pleasure to welcome you to this lecture today. In April of last year, I joined my fellow Keck Science presidents, Laura Tidens of Scripps and Hiram Shodash of Claremont McKenna, to announce the appointment of Dr. Ulysses J. U.J. Sofia as the Weinberg Family Dean of the W.M. Keck Science Department. I'm going to use UJ most of the time. We chose UJ because of his broad breadth of administrative experience, from department chair to associate dean to the director of research of important scholarly endeavors. These are all characteristics that we look for our new Keck Science Dean. But first and foremost, we were looking for a scientist of first distinction. And UJ, we found that. Dr. Sofia received his BA from Wesleyan University in astronomy with high honors, and his PhD in astronomy with the concentration in physics from the University of Wisconsin-Madison. UJ began his career at Whitman College in 1998 and received the inaugural William and Diana Deschler Endowed Chair before departing to become the chair and professor of physics at American University in 2009. Throughout his academic career, he has focused his teaching in physics, astronomy, and astrophysics. He was awarded the A.E. Lang Award for Distinguished Science Teaching at Whitman College in 2003. His research focuses on solar activity predictions, interstellar dust, and the interstellar medium. Dr. Sofia has received many external grants and published important work. His administrative experiences include serving as Associate Dean for Research at American University and holding positions as the Director of NASA's District of Columbia Space Grant, Consultant to NASA Flight Dynamics Division, and Associate Director of Goddard Planetary Heliophysics Institute. Since arriving here, UJ has become a well-known face and voice in the Pitzer College community. We are very excited to welcome you today and look forward to learning from your distinguished scientist lecture entitled, "The Sun, the Scientific Method, and the Corruption of Science." Please join me in welcoming Dr. UJ Sofia to the podium.
Can everybody hear me? Ooh, yes. Okay, welcome. Thank you all for coming out on this gloomy day. So this is a picture of the sun actually from today. There is a nerdy website called spaceweather.com that you can go on to any day and see what the sun looks like today. I do that quite often. You don't have to. Most of what we know about the sun we get from looking at it, right? We can't really probe it very well. We can't go, we don't have any satellites that have gone into the sun. It wouldn't last very long. We can get some information about its magnetism. We can get information by looking at it in different sorts of light. But we can't really probe most of the sun itself. There's a lot going on underneath the surface that we try to figure out about from what we see on the surface. On days like today, there's not a whole lot going on to tell us what's happening. But if you look a little more closely at the surface of the sun, you can see, and this is not today, but this is on a regular day, that the surface of the sun is constantly moving. There's sort of a boiling up of gases from underneath. And this tells us a bit about the way that the sun is heated, how much energy is coming out. You can see the clock on the right, it's sped up a little bit. But on a normal basis, the surface of the sun, there's convection that's bringing heat up. And each one of those white dots that you see up there is about the size of Texas, just to give you an idea of. So these are large masses of gas that are coming up. So that's all the time. Sometimes, unlike today, the sun has some spots on its surface. And so that tells us something about what's going on underneath the surface. Okay? We can learn, again, more about what's happening underneath by watching what's on top. Here's an up-close and personal picture of a sunspot. This is from about a decade ago. And again, those bright spots, those bright yellow spots, are all about the size of Texas, which gives you an idea of how big the sunspot is itself. Those sunspots are very high in magnetism, and I will talk to you a little bit later about what we can learn about magnetism on the sun from that. So that's what we can get from the surface. That's sort of what we see on a regular basis. We know a little bit about what's going on inside the sun from neutrino experiments. Neutrinos are particles that are formed in nuclear fusion. So nuclear fusion is what gives the sun its energy and all stars their energy. And part of that process produces these little particles called neutrinos, which are odd little buggers. They are very low in mass. They don't have a huge amount of energy, but what's really interesting about them is they don't really interact with matter very well at all. So they just travel through space as if there's nothing impeding them. There are trillions, literally trillions of these things going through your body every second from the sun. But they don't mess with you in any way because they don't see you. They just travel straight through you. They travel straight through the Earth and come out the other side. Your average neutrino would not notice 100 light years of lead as it passed through. Okay, these things do not interact with matter very much at all. Yet, scientists still try to capture these things so we can understand them a little bit. This is one of the older neutrino experiments. This is a tank of tetrachloride, basically dry cleaning fluid, in a gold mine in South Dakota. And a dry cleaning fluid is a tetrachloride, 4 chlorine atoms that are put together. And every once in a while, extremely rarely, one of these neutrinos will interact with one of these chlorine particles just in the right way and turn it into an argon. So it goes from a chlorine to an argon if there happens to be the right interaction, which is rare. That is 25,000 gallons of dry cleaning fluid. Every week, they find about 6 neutrinos that have turned chlorine into argon atoms. There are trillions going through you every second. Imagine how many are going through all of that, and they get 6 conversions. Okay? So we learn a little bit about what's happening in the center of the sun right now based on what we see from neutrinos, because those neutrinos that are formed in the center of the sun shoot right out of the sun without even noticing that they're in the center of the sun. And just to give you an idea, the sun has a radius of about 700,000 kilometers, or about 500,000 miles. Okay, so those neutrinos come out at nearly the speed of light, unimpeded. So we see them a few minutes after they're released from the sun. Okay, so let's go back and talk a little bit more about sunspots. Again, the relative size of the Earth, you can see by that little dot there. These things are quite large. And again, they're highly magnetic. The way that we think they form is starting with a magnetic field. So if you think of about a basic magnetic field, you have a bar magnet up here, and you have lines going from the north to south, field lines. So you see that nice, just sort of simple north to south field line, right? Shavings on a bar magnet, iron shavings on a bar magnet is what you're seeing there. Okay, we think that the sun starts off with that simple magnetic configuration where you just have a nice north to south polarity. So there's the sun, and I'm going to start this off. Oops, that's not the way I'm going to start it off. Start this off. Let me see if I can stop this. Yes. Okay, and we have just that nice field polarity from north to south. The outer regions of the sun are ionized. They're basically charged, right? Electrons are taken off of atoms, so you have positive and negative charge. So those magnetic field lines actually are attached to the material in the outer layers of the sun, okay? Unlike the Earth. The center of the sun, around the equator, rotates faster than around the poles. Okay, so you have these straight field lines that are attached to the material in the sun, but the equator is moving around faster than the poles are. So far, so good? So what's going to happen is the field lines are going to start getting twisted. So they start getting twisted around the center, and they go from vertical to horizontal, and they get so crowded as they get twisted up that they start popping out of the surface of the sun. Okay? So This looks like it's a mess. If you actually saw a magnetogram of the sun, it's worse than this. The sun gets incredibly complex incredibly quickly when those field lines start getting twisted up. Okay, so when you get the twist and you get some of these lines popping out of these magnetic fields popping in and out of the sun here, like there and there, what's happening is that, we're going to go under here, that you have these loops of magnetism popping through the photosphere of the sun, the part of the sun that we see, that yellow part. As they go through, they slow down the material in the areas where they're popping through. So right around here, they're slowing down that material, slowing it down, cools it down, and we see it as a dark spot. You're going to see the magnetic field pinching off here and some material flying off into space. That's a solar flare. So solar flares, which you may have heard about, are associated with sunspots. So far, so good? Okay, so if we look at the number of sunspots, which is on the y-axis here, versus time, you'll see that there's a regular periodicity of sunspots going from almost none to peaking to almost none to peaking. It's about an 11-year cycle. Sometimes the cycle is as short as 10.5 years, 10 years, and it can be as long as 12.5 years. But on average, it's every 11 years you get a peak in the number of sunspots that are on the sun. So you get the lines twisting up. As they're twisting up, more and more of them start popping out of the surface of the sun. You're getting more and more sunspots forming. And then as you continue to twist those field lines, they start to break up. They're twisted so much that they start breaking apart, and then you start losing the number of sunspots. So you're going down on the side beyond the peak. When you get to the point where the field is so broken up that there's no longer any coherence to it, it disappears and it reforms as that nice simple north to south polarity, and the cycle starts over again. Okay? When that happens, the sun switches its poles. So every 11 years on average, the north and south magnetic poles of the sun switch. Okay? You can see that the solar activity is not the same from peak to peak. This is not working. There we go. That the peaks are different sizes, they're different breadths. You have short, sort of fatter ones, you have tall, skinnier ones. So the sun is not always doing the same thing, which is not overly surprising. On a longer time scale, so these are in thousands of years, 2,000 years, negative 2,000, negative 4,000, negative 6,000. So we're looking at about 12,000 years worth of time scale here. People have tried to look at the solar activity over that time period. Obviously, people aren't counting sunspots in this graph. In the previous graph, people were actually counting the sunspots, which made that graph. Here, we're relying on things like ice cores or tree rings to tell us how active the sun was. You can look at isotopes in those and see the activity of the sun. And some people think that they see a periodicity of about 9,000 years in here. Take it with a grain of salt. We don't know exactly what the sun is doing over long time periods, but there is some variation there. Okay, so naively what you might think is when there are sunspots on the sun that we're getting less energy from the sun, right? There are dark spots, so you're not getting as much light from the sun, so maybe the energy is going down, right? Not at all the case. Exactly the opposite is true. When the sun is active, when you have those dark spots on the sun, you're actually getting more energy from the sun than when it's not active. So we're going to start off here. This is an image from the SOHO satellite. Talk about SOHO a little bit more in the near future. SOHO is a satellite that's been up for 22 years, taking pictures of the sun in visible light, and this is visible light, black and white, but visible light, and it's going to switch over to X-ray, okay? And when it switches over to X-ray, it will turn some funky colors. Oop, there we go. So you can see some sunspots there. There's some activity on the surface of the sun. You can see them forming. It takes 27 days for the sun to rotate once, just to give you a time scale. So in this picture, where there are the bright spots in the X-rays, these are different wavelengths of X-rays, that's where the sunspots are. So when there's darkness in the visible light, those regions that are cooler because the magnetic field is popping through the photosphere, around that you actually have heating of material from the magnetic field. And it heats it enough that you're actually getting most of your light out in X-rays instead of visible light. X-rays are more energetic than visible light, so the overall amount of energy coming out of the sun increases when there's more activity going on. That make sense to everybody? Okay. And here are some pictures of what's going on in different energetic wavelengths of light when there's sunspots. So here is a magnetic field that's going between two sunspots. This is an X-ray again. And you can see there's a loop of material that gets caught in that magnetic loop, and it gets heated up and it's bright. Here's a bigger version of that. In this picture, the sun is underneath this white circle. And you can see some of these loops go very high up. That's a lot of material and a lot of energy coming out of there. There's another one. These are called prominences that are coming off here. And this is also going between two different spots. All these are in high energy photons, high energy light. So you can see that there's a lot of energy coming out of here. Some of those prominences, some of those loops between sunspots break off and go into space. And that material can come toward the Earth. When that happens, we can actually get measurements of the amount of material that comes toward us. The sun will be over to the left here. This is the Earth's magnetic field and the Earth. So the Earth has a nice simple magnetic field around it. Our magnetic field protects us from most of that radiation that's coming off of the sun that gets blown off in those magnetic loops. So most of it gets deviated one way or the other. But when there's a lot of that material coming toward us, it gets caught in the magnetic field and can be slammed into our poles. So our magnetic field can catch some of it, and then it gets diverted down and slams into our poles. Doing okay? That results in an aurora, both on the north and south poles. So here's a picture of the aurora from space, and you can see this circle of light. That is where particles that got caught in the magnetic field are slamming into the poles. This is the North Pole, slamming into the pole. When those particles slam into the atmosphere, they excite atoms, which release light. Okay? So we can actually see this when the sun is quite active. Right now, the sun's kind of on a downturn, so we don't have a lot of activity going on. Okay, so that's kind of what we can get from the sun just by looking at it very simply. I'm going to shift gears a little bit and talk a little bit about climate change. So here are temperatures recorded on the Earth for about the past 100 years. When you see blues and yellows, yellows are sort of average temperature, blues are a little bit low, reds and oranges start being hot. You have Africa in the upper right, America upper left, Europe bottom right, Asia bottom left, and Oceania almost up top. And what you can see as you go through the years, those colors get redder and redder and redder. Okay? So, should we do that one more time? Start off in 1900, you've got lots of blues and yellows, a red once in a while. As we go on, Industrial Revolution, now we're almost all yellow. Yeah, you're still getting some blues. Now we're getting a little more yellow, a few reds popping up. Now we're getting orange, reds, 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 reds. No blues anymore. Okay? So that is a measure that our climate is changing. Oftentimes, people will talk about we're not having climate change, or they'll talk about global warming. Global warming is a term that we should never use. It is overall a warming of the globe that's occurring right now, but some places will get cooler with climate change, some places will get warmer. Overall, it'll be warmer, but let's talk about climate change rather than global warming, okay? That way, your politicians can't bring a snowball into Congress and say that there is no such thing as global warming, which you have all seen has happened on TV. So global climate change is taking place. And this is not something that happens on a year. If you have a particularly cold year or a particularly warm year, that's not climate change. Climate happens over decades. And what we've seen is a change over decades. Okay, so this truly is climate change occurring. What are the reasons for climate change? Well, some of the major factors are the sun, which is why I'm bringing up climate change. So the sun is the only real source of energy that heats the Earth. Okay? There are some internal heat sources of the Earth. There's some radioactive decay. That's why we have volcanism and things like that. That contributes almost nothing to the atmospheric temperature, to the environmental temperature. So really the only thing we have to worry about when we're talking about climate change or the climate in general on the surface of the Earth is the sun as far as an input factor. Atmosphere, composition dynamics will affect what's going on with climate. Circulations of the oceans have an effect on climate, and climate has an effect on circulation of the oceans. Carbon dioxide absorption occurs in the ocean, and the amount of that going on affects what's going on in our climate. As we lose ocean, we also lose some of the capability of absorbing carbon dioxide and methane in the ocean. As we gain it, we do have more ability to put more of those substances into the oceans. Albedo of ocean and continental surfaces. So albedo is just reflectivity. So you have more clouds, that reflects more light. You have more snow, that reflects more light, things like that. And aerosols, basically little bits of things in the air. From volcanism, you have ash, decay. Rice paddies are one of the biggest sources of methane in the atmosphere, decay from that. Biological, cow gas, and anthropogenic are putting a bunch of industrial pollutants into the air, okay? We know that greenhouse gases are going up, whether from any of those factors that we just talked about. Carbon dioxide is mostly from humans. Methane is also mostly from humans, but in a less direct way. And nitrous oxide also. These are all major greenhouse gases. Carbon dioxide is the one that you hear about most, but both methane and nitrous oxide per atom are worse for global climate change than per atom of carbon dioxide. We just talk about carbon dioxide a lot because that's the one that we have a large effect of with our, well, we have an effect on all of these, but carbon dioxide is the one you hear about most. We talked about the change in temperature already, and here's just another graph of that, same thing from about 1900 to 2000. And you can see that our temperatures have gone up by an average of about 1 degree, a little bit more than a degree Celsius over that time period. That line is going up more steeply with time, and it's predicted to go up more steeply as time continues on. Okay, so let's talk a little bit about the sun again, getting back to that. Can the sun actually affect, or can variations in the sun actually affect our climate? We think so, but there's still dispute about this. In the 17th century, there was a time period where there were very few sunspots on the sun. So here again is number of sunspots versus time. And there's a period here from about 1640 to about 1720 where there were very few sunspots on the sun. And you can see how many cycles there should have been in between there. We should have these peaks coming up every several years. But there were very few measured sunspots. It wasn't zero, but it was close to zero. Over that time scale, nothing was happening with greenhouse gases. So anything that you saw happening in the climate maybe could be attributed to the sun over that time period. The sun itself, other than having few spots, had low auroral activity, so not surprising we didn't have a lot of auroras over that time period because I told you that auroras are associated with sunspots. No visible corona during solar eclipses. So right now, if you were to go and watch a total solar eclipse, how many people watch a total solar eclipse this year? Excellent. When you saw that, you saw the corona around the sun, right? You saw that bright halo around the sun. That's 2 million degree gas that we always see around the sun. We're not sure how it's heated. We think it has to do with the magnetic field, but it's always there when we look at the sun, except over this time period. There was no visible corona over that time period, which again relates to the magnetic activity up on the surface of the sun. The rotation rate and differential rotation. So I told you that the equator of the sun goes around faster than the poles. The ratio of the poles to the equator changed over that time period, and the overall rotation rate of the sun changed over that time period. Slowed down a little bit. And the solar diameter, the size of the sun, as best we can measure it, which is not fantastic, but you can make some measurements from solar eclipses, was bigger than it is now. So the sun was somehow fundamentally different over that time period, and so was the weather. The weather was particularly cold over that time period, and a lot of people talk about the fact that a lot of art that was done in that era shows things like lakes and rivers that are covered over. Apparently this is the Thames that is frozen over in London, which almost never happens. But for years and years and years, they had ice festivals on the Thames over this time period because it was cold enough that they could do that. Okay? So there was something going on with weather, making it colder. There was something going on with the sun. As I said, there is controversy about whether those two things go together. They relate pretty well in time. It looked like it actually started getting cooler on the globe about 10 years before the sunspot activity slowed down. And it looks like that cool period actually lasted about 10 years longer. To me, that's not a reason not to believe that the sun was responsible. The sun could easily have been winding down before. Basically, some of the energy from the sun could have been winding down before all the sunspots disappeared. And same thing, it could have come up late. So there's relatively good evidence that these two things are involved, and therefore the sun actually can have an effect overall on what's going on with climate change. Okay, so solar physicists, if you're a solar physicist, you want to measure, in order to understand what's going on with the engine of the sun that's producing the energy and may affect climate, you want to know what's going on with the solar radius, the luminosity, which is just the overall energy output of the sun, and the temperature on the surface of the sun. If you know those three things, you can get a very good idea of what is happening as far as the energy source of the sun. If you can watch those three things go up and down together, vary together, you can get a very good model of what the sun is doing overall. Okay? If we understand that, then we have a better understanding of what the sun is doing for climate. Right now, most climate models don't have much of a variation with the sun. They don't take into account the fact that the sun can vary and put out different amounts of energy. Okay? That's possibly a fundamentally large error within these global climate change models. When I say large, not large enough to counterbalance what we've done by putting greenhouse gases into the atmosphere. Some people like to say, oh, the sun is responsible for all the differences that we see in climate change. Absolutely not. No matter what is going on right now with the sun, it cannot have done everything that we're seeing going on with global climate change. The sun might have an effect. We don't know whether it's a positive effect or a negative effect. In other words, any solar variability that's been going on over the past 100 years, has it actually moderated our temperatures a little bit or made this effect worse? We don't know. But whatever it is, the greenhouse gases are definitely making our temperatures go up overall globally in our climate change. So basically what we hope to do with some of the research that I'm doing is understand how the sun varies, how we can measure that, make sure that goes into climate change models so that we can get a better idea really of what our greenhouse gases are doing. How are we doing? Okay. So I'm about to put something up that is just purely to prove that there's like scary science behind it. Whee! Those are the equations that we need to solve in order to do this. Yay. Okay. As I told a group on Saturday, you're supposed to lose 5% of your audience every time you put up an equation, so most of you should be gone by now. Okay. So one of the things that I'm involved in is actually trying to figure out one of these parameters. I told you temperature, overall luminosity, total output of energy, and radius. The part of this that I'm involved with is trying to figure out what the sun's radius is. Very precisely. We want to know how the sun's radius changes so that we can understand the engine producing the energy totally. So the sun is small in the sky. Most people don't realize actually how small the sun is. So if you took a pea, and I hope you all do this at some point, take a pea and hold it at arm's length, you can actually cover up the sun with that. It's small. The sun is tiny, tiny, tiny in the sky. Okay. You're unimpressed. It's tinier than you think. Okay. And actually, those of you who saw the eclipse, when you were looking at the sun through your glasses, you kind of notice how small it was, probably, smaller than you think. And the weird thing is, I'm on a tangent here, the weird thing is that the sun and the moon are almost exactly the same size in the sky. That's why when an eclipse happens, they cover each other. But people have the impression that the moon is much bigger than it is. It's not. You can also hold a pea out at arm's length and cover the moon. Try it. In fact, it's safer with the moon, so I recommend that. Okay. But the sun is small. It's only half a degree in the sky. We measure things in astronomy by degrees. So we're here on Earth, and something is that big, it's that angle in the sky. The sun is half a degree, which is like that angle in the sky, okay? Not many things are as big as the sun, which is half a degree, so we measure most things in terms of arc seconds. There are 3,600 arc seconds in a degree, okay? An arc second is a very, very, very small angle. We good? More than 1 million of them in a circle, okay. In order to actually understand what's going on with the variability of the sun so that we can understand this energy production and variability better than we do, we need to be able to measure that angle of the sun, how big it is in the sky, to 1/10,000th of its size. Okay, so we have to measure it very precisely. If the sun varies, and it probably does, it's by a very little bit. Okay, still makes a big difference in what energy it produces. In order to do this, you need to go into space. You need to go into space because our atmosphere blurs images as viewed from the ground. So if you see a star twinkling in the sky, that's our atmosphere blurring it, okay? We can't do that. When we're looking for something that's 1/10,000th of half a degree in the sky, you can't do that. That blurring destroys it. You have to get above the atmosphere to be able to make these observations. You need, I will argue, a metrologically designed instrument. That means that you have an instrument that has in its observing system some invariant thing that you can relate all your calibrations to. Okay? There is something fundamental in the optical system of, in our case, a telescope, that when you get an image back, you can relate and calibrate everything back to that thing that you know exactly what it is. That's how precise these measurements are, that you need to specifically have an instrument designed to do this in order to do it well, I will argue. And then you need rigorous calibrations. Even when you have that in your optical system, it's still very hard to get back to the level that you need in uncertainties. Doing okay? Okay, there are 2 instruments that have claimed to have measured the solar radius and its variation over time, or lack thereof, as it were. The first one is SOHO. SOHO is the satellite I showed you the pictures of that were both in visible light and X-ray light. SOHO's been up there for 22 years, doing a great job. There's a Doppler imager on that. A Doppler imager is looking for changes in motions toward us or away from us. Has nothing to do with radius. The SOHO instrument, when it went up, it was about $1 billion in cost. That's actually more than $1.5 billion in today's dollars, but there's also been a lot of money, hundreds of millions of dollars that have gone into the support of the data analysis and running of the instrument over the years. So it's about a $1.5 billion instrument. So far, it's still going. It initially had a 3-year lifetime, and they've kept it going for an extra 19 years now. Not metrologically designed. This is not an instrument that has anything fundamental in its observing system for you to calibrate to. Okay. And this instrument, not surprisingly at $1.5 billion, has supported hundreds of scientists throughout the years. Lots and lots of people have gotten data from this and gotten money to analyze data and have gotten their postdocs and PhDs and things like that paid for with this. Okay. The other instrument, and that's a picture of SOHO at the top, a drawing. The other instrument is the Solar Disk Sextant. The Solar Disk Sextant was specifically designed to look at the diameter and the shape of the limb of the sun, the edge of the sun. Long baseline means that it's meant to run over many, many years. It was originally designed to work for about 25 years. Low cycle. SOHO's up all the time taking pictures constantly and has been for 22 years. The SDS flies every few years at best. Okay, so it's low cycle. We don't take observations very often. Low cost, $1.5 million. a bargain, 1,000 times cheaper than SOHO. 24 years old at this point, at least in its current configuration. It is metrologically designed. It was designed specifically to measure the diameter/radius of the sun. Okay, so it was designed for this purpose. And it has supported a grand total of 5 scientists over its 24 years. Okay. So what did SOHO find out? So the bottom line is SOHO found that over one of those solar cycles that there is no variability in the radius of the sun, that the sun did not vary over that time period. What this graph shows you is changes in the size of the sun on the y-axis versus time. And those things are all over the place. That's because the instrument required a huge number of corrections in order to get their answer that there was no variability. So basically, what they said was, if you take those data and you apply theoretical corrections to them, you end up with a perfectly flat line. I'm skeptical. And what they said was, so again, we're measuring things in arc seconds, so the size of the sun varied by about 4 arc seconds here. You need a precision of about 1/10 of an arc second to actually measure the variability of the sun. So basically what they've done is they've made corrections that are 40 times bigger than the thing that they're trying to measure. Possible? Maybe. Maybe. But that turns into, and again, the scale goes from 2 arc seconds to -2 there. This is a paper that shows the results. And now you're talking about the scale is, the tick marks are 0.05 arc seconds. So this is what it's collapsed to after they got rid of, when they did all their calibration, supposedly. And it turns out to be a relatively flat line, and they call it flat, no variability. We good? Are we dubious? Okay, that's good because I led you there. You should be dubious. An instrument that was not designed to do this, it's a very, very difficult thing to do. And you're making corrections that are so much bigger than what you're looking for, it's problematic. Now for the SDS. So the SDS is our cheap little instrument. You'll see how grandiose it is up there in the upper left-hand corner. We taped cardboard to it so that when it crashes a little more softly than if you don't. It has foam that we just stuck on there with duct tape to protect it from the sun as thermal control. These instruments are, they're like they were built in your basement or something. They're amazing that they work so well, but they're not glitzy, they're not glamorous. Here's the payload itself, the instrument, the telescope's right in there. Here's the gondola that flies on the balloon. That is as tall as I am. That is the truck that's holding the balloon down there. And then that was the balloon that just went up, just to give you an idea of how big the balloon is. These balloons are enormous. So ours flies on a balloon. It doesn't fly in space. It's a lot cheaper. That's part of the reason it was only 1.5 million. And so we had several flights of the SDS. And again, one of the things that makes it special is it is metrologically designed. And again, this is just to prove that it is metrologically designed. I don't expect you to understand it. But what we do is we have a wedge in there that creates 2 images of the sun at the focal plane. And the thing that we know precisely is how far those 2 images are spread apart from each other. And so we can relate any distortion in the focal plane to that and get our answer out. We found that there's variability in the radius, unlike SOHO. So how sure are we of that? The sun goes around, the Earth goes around the sun goes around the Earth. The Earth goes around the sun in a slightly elliptical orbit, and it changes its distance from the sun over the course of a year by about 3.3%, so not very much. We were able to measure in 20 minutes in October as the sun was approaching the Earth, or the Earth was approaching the sun, we measured a change in the apparent size of the sun. As the Earth approached the sun, we actually saw the sun apparently getting bigger. You get closer to something, it looks like it's getting bigger. We can measure that in 20 minutes. 0.01 arc seconds we were able to measure. 0.01, okay? So that's a really high precision, obviously. All those little dots are our data. Each individual one is not very good, but average it over those 20 minutes and put a line through it, it's exactly what's predicted from our motion toward the sun, okay? Okay, so we found that the sun does vary in radius. Here is a picture of our results over time. We go back as far as 1993. The black dots are our data. You can see with the error bars on them, and our last flight was in 2012. And our data show that it does vary. The red line is actually the solar activity, and it varies in a way that's slightly off sync with the solar variability, which is actually something that we would expect. We'd expect the magnetic field, as it gets twisted up, to create some pressure to expand the atmosphere a little bit. And then as you start getting sunspots, for that pressure to be released and the sun to collapse a little bit. So we're sort of seeing exactly what one would expect. However, it does not agree with the 1,000 times more costly SOHO. So our results say that the solar variability actually could be important to global climate change. Publications of the SDS results. So interesting enough, SOHO published its paper that said that there's no variability in 2010. This is something I have never talked about because you never talk about your failures. I am openly displaying failure to you, although it eventually worked out okay. We tried to publish our results in Solar Physics. This is in 2014, in the journal Solar Physics, with an impact factor of 2.862, just to give you an idea of the quality of the journal. And it was sent to a scientist, and it was rejected. And it was rejected because it disagreed with the result from SOHO. There was nothing wrong with our analysis. There was nothing wrong with what we did. There was nothing wrong with our instrument. It just disagreed with the previous result. And that's why it was rejected. We tried to go to the editor and say that's not a reason to reject a journal article. And he refused to accept it. Oops. Then we went to the Astrophysical Journal, higher impact factor, more general in science. Based on its, judged on its science again, exactly the same result. There are hundreds of people out in the community that rely on the results of SOHO to pay their salaries. Finally, we sent it to monthly notices of the Royal Astronomical Society, which has an impact factor substantially higher than the first place we sent it to, and it got accepted. And when we sent it to monthly notices of the Royal Astronomical Society, we said, do not send it to a scientist. Send it to somebody who understands instrumentation and calibration and whether this instrument actually made the measurements correctly. And that's what they did. And that was what was more important to us anyway. Did we do these measurements correctly? If the answer is yes, then we came up with something that's fundamentally different than what was come up with from SOHO. Okay? Twice we were rejected because our results didn't match a previous result. Okay? That's where the corruption of science, part of where the corruption of science comes in my title. So scientific method. Think of an interesting question. Does the sun vary? Formulate a hypothesis, develop testable predictions. We can go and make the measurements, gather the data, and then if you need to, refine and alter, expand, and reject the hypothesis and go again. That's where we got stuck, right? We weren't allowed to sort of go through this loop. This is where we should be now. Going through this loop saying, hey, one instrument said that the sun is not varying. Another instrument said that the sun is varying. Fundamental disparity. Something is wrong somewhere. Is it us? Maybe. Is it SOHO? Maybe. But we got to figure it out. Right? You don't say, you don't agree with previous results, so we're not going to let that out there. We're going to continue on with corruption of science. There was a big hoo-ha at the end of last year in December about 7 words that were banned at the CDC, Center for Disease Control: diversity, fetus, science-based, vulnerable, evidence-based, transgender, entitlement. The last word on this is that the CDC banned this themselves because they were afraid of their budget being cut if they used these words in their request for budget allocation. Some people say, well, okay, so they weren't really banned, so it's not so bad. No, they were banned. If this is what you have to do in order to make sure your funding is not cut or not cut severely, these words were banned. And it is a corruption of science, because if this is truly what needs to be said, it's not being said, and it's money holding you hostage. The word climate change was removed from websites at the EPA, the State Department, the Department of Energy, Department of Health and Human Services, Department of Agriculture, and NASA. This has all happened in the past year. Okay? Did global climate change go away? No, but we're trying to scrub it and change basically what is being said about it. Data have been removed from some of these websites or made much more difficult to get to on global climate change. Links to state sites about global climate change are no longer accessible from some of the national websites, from our national government websites. And Obama's Clean Power Plan was removed from federal websites. So we're taking away the narrative of what's out there by just scrubbing websites. Again, doesn't mean it's not there. We're just changing what we're saying about it and trying to hide some of what the reality is. We're no longer having the debate that we need to about what science is. Who's in charge? The president. We know his feelings about science overall. I think that's relatively clear. EPA, Scott Pruitt, well-known climate change denier. Rick Perry, Department of Energy, well-known climate change denier. NASA, Jim Bridenstine hasn't been fully put into office yet. He's still going through the process of being nominated, but will likely end up there. Big climate change denier. Council on Environmental Quality, Kathleen Hartnett, climate change denier. That is a White House office to advise on climate change. Science advisor to the president, there is none. Currently, there's a political scientist in his 30s that is filling that position just because he has the position that it falls to when no science advisor has been posted. Vaccine panel, thank God this didn't go through, but there was talk about a vaccine panel where Robert Kennedy Jr., so it's both sides of the aisle, who is a vaccine autism person, was going to be the head of that panel. That panel probably is not going to happen. Committee on Environmental and Public Works in the House, James Imhoff, snowball. He's the snowball guy that brought the snowball into Congress and said climate change doesn't exist. Science, Space, and Technology, Lamar Smith loves bringing in quotes from NSF proposals or proposals to other science agencies, take them out of context, and try to make them look ridiculous. Our only hope, Bill Foster, PhD in physics, the one PhD scientist that is in the House or Senate right now. Okay? There is very little scientific knowledge in our government right now at the House and Senate level, and what's going on at the top science agencies as well as in the White House is not very promising. Okay? Who's educating people on science? This is kind of interesting. This shows the number of scientists interviewed or quoted on different networks, news stations, and segments about scientific research. Fox has none of either, and PBS does pretty well in both. So the people that are watching Fox and the people that are watching PBS are getting two very different ideas of what's going on scientifically in the world. Okay? And a lot of people, this is where they get their information from about science. This is on my door. Comic relief for a second since we've been a little heavy. So this is, you're supposed to be more worried as you go to the right. How worried should you be if you see a local reporter interviewing scientists about breaking news story by field? want you to notice that an astronomer who studies the sun is the most worrisome. No worries of that on Fox. Okay, and this was funny because I was just looking at the Chronicle of Higher Education a couple days ago, and there was an article called The Intellectual War on Science. I thought, ooh, this is going to be some interesting information for this talk. It turns out that they're talking about the liberal arts, colleges and universities attacking sciences, which was fascinating. And the quote that I took out is, the most frequently assigned book on science in universities, aside from a popular biology textbook, is Thomas Kuhn's The Structure of Science, Scientific Revolutions. How many people have read that? Me too. The 62 Classic is commonly interpreted as showing that science does not converge on the truth, but merely busies itself with solving puzzles before lurching to some new paradigm that renders its previous theories obsolete, indeed unintelligible. Though Kuhn himself disavowed the nihilist interpretation, it has become the conventional wisdom among many intellectuals. So apparently, even within the academy, we are attacking the sciences at certain levels. Finally, last but not least, scientists themselves are corrupting science to a certain extent. Poor science, science that is not properly done. So the whole debate about autism and vaccinations, that was a paper that was done with 12 people. 12, sample of 12. Okay, that is not a sample, and it was not a controlled experiment. It's hard to control an experiment with 12 people. Okay, but that changed for years, this debate on whether vaccines cause autism, and have resulted in many people not being vaccinated. Sensationalism in news release. Just this past week, somebody said, I read that the sun is going into a Maunder minimum. We're about to go into this deep cooling period. There's a lot of debate about that. There was a big thing a couple of years ago about major flares coming from the sun, which are going to disrupt the power grids and turn off the power in the Earth for 10 years. Didn't happen. So we don't do ourselves any favor when we over-sensationalize things. And when there's something sensational, but then gets corrected, which often happens when there's a sensational story, the correction never is newsworthy. So you never read about that. So there's a lot of misinformation there. Constantly changing conclusions. My favorite is coffee good for you or bad for you this week? Right? You hear different foods constantly. It's good for you, it's bad for you. Biased peer review. So I'll go back to the SDS trying to get its results published and having our little 5-person team, $1.5 million versus the 1,000 times more expensive Soho that supports hundreds of people. And finally, earmarks. And that goes on the scientists as well as the government. Scientists go for their earmarks. They want their special pet projects. What that is a few people, oftentimes uneducated people about science, determining what is going to be funded with your tax dollars. Right? It's oftentimes not scientists deciding or choosing what is the most important thing. It is people that have nothing to do, go back to the slide about our politicians, people that know nothing about science that are deciding what our priorities are and where your money should be spent. And on that happy note, I just want to thank my collaborators on the science. Thank you for listening, and then give you the references to the sites for my images. Thank you.